Welcome back. So today we'll start a new topic on magnetism, and in the next few lectures we'll be working on the concepts of magnetisms. So for today we'll be talking about magnets and magnetism and magnetic field, and also we'll touch on magnetic force and some of its applications. So let's jump in here. So one of the amazing phenomenon that you can explain well with physics is the Northern Lights. It's so beautiful, stunning, and we're going to learn something about it today. But if you click on this link on the lecture note, there will be a video on the Northern Lights, the display of Northern Lights. Okay. All right. So I don't know about you, but my kids, when they were a little bit younger, 3, 5 years old, they love to play magnets. And they can form different shapes. They can building houses and all the stuff. And they fought against each other to play with those. Um, so this is because these things they can attract each other. You can put them together, and a lot of sort of fun things you can do with them. All right. So for magnets, a magnet has two poles. So this is similar to charges. So when the poles they are close to each other, if you have opposite poles of the magnets, they will attract each other. If you have the same poles close to each other, they will repel each other. So again, this is very similar to charges, but in this case, we call North Pole and the South Pole for the magnets. Okay. So like poles will attract repel each other, opposite poles will attract each other. Okay. Unlike charges, if you have magnets, you can break a magnet into two pieces. So if you do that, you actually have now for the new two pieces, there will be a south pole and a north pole again. So that means you generate a north pole on this side and then generate a new south pole on this side. Okay, and then you can further divide these ones into smaller ones, and each small magnet will have a north pole and south pole itself. Okay. But for charges, if you divide um, charges into smaller ones, it gets smaller and smaller. Okay, so it will not have like a new positive, negative charges in that sense. So it's a little bit different. The Earth, our Earth itself is a giant magnet. Okay, so we know that you can use a compass to guide you to the North Pole because of the Earth's magnetic field. However, if you use a compass only, you're not going to get to the North Pole because the Earth is a magnetic South Pole, which attract the North Pole of your compass. Okay, so and then that North Pole is pointing towards north, but it's actually about 200 miles away from the geographic North Pole. Okay, so there's a little bit off there, but it's pretty close in that sense. Okay, all right. Earth's magnetic field actually have reversed its polarities a few times over the history. So when that happens, it actually, on average, it takes about 450,000 years for that to happen. Um, and it's anything between about 100,000 years to 1 million years in that range. But on average, it's 450,000 years. Okay, and the most reversible um, most reversal are estimated to take about, so for if the reversal happens, it takes about 1,000 to 10,000 years. So when that happens, so it would be something look like this, and then your compass will not likely work very well because now the magnetic field is quite distorted and rather than uniform as we have right now. All right. So the evidence of Earth's magnetic field reversal, it's on the molten rocks, where when that happens, when the reversal of magnetic field happens, then you actually with these molten lavas, they were liquid initially and then line up with the magnetic field of the Earth at that time, and then when they solidified to be rock, then that magnetic field is recorded there. So if you look at through the molten rocks through different histories, then you have the memory of the Earth's magnetic field at that time. Okay, so that's the evidence there. All right. Now let's talk about a little bit of fundamental of like what causes magnetism. Okay. So normally electrons surrounding an atom, they actually um, each one surrounding an atom, the actually will so electrons, we know they are charged particles. So when they have that, they create actually currents. And then currents, we'll learn it in a couple of slides later, actually produce magnetic field, okay? But since there are so many electrons here for an atom, or if you compare to like from atom to atom, then the orientation of the magnetic field by each electron is actually random. So they kind of cancel out, okay? However, there's certain material you can actually have their electrons, some of the electrons moving in the same direction, so they have that tendency of lining up the magnetic field produced by those electrons. Okay, so for those materials, we call them ferromagnetic materials, and there are not many of them. Um, iron, cobalt, nickel, and gadolinium, they are the ones that have this effect. Okay, so they are called ferromagnetic materials. There are also other materials that if you have external magnetic field present, the domains inside the material will produce a stronger magnetic field, but once the external magnetic field is removed, then those domains orientation become random again. So that magnetic field actually is lost during that after that. Okay, so those are called paramagnetic materials. Now, for ferromagnetic magnets, you can create magnets with those materials, and but if you heat the temperature of the materials up over 770 degrees Celsius, then the domains become random oriented again. You will lose majority of the magnets in that case. So that temperature, 770 degrees Celsius, is called the Curie temperature. The way to make ferromagnets is if you have material made of one of the elements, for example, iron, you can put the iron into the magnetic field here, south and north pole here, and then you'll heat up the material. So then the domain orientation inside will be rearranged according to this outside magnetic field. So on the originally, it's quite random. Then after you heat it, it will be becoming more uniform in one direction, and then at a certain time later, it becomes very uniform in that case. So then you have now a magnet itself in the iron material there. Okay. So as I just mentioned earlier, that currents actually produce magnetic field. So that was first discovered by Danish scientists about 200 years ago. So where he observed that in the lab accidentally that actually when the current goes to a wire, then a compass nearby has changed direction. So that shows you that a magnetic field is produced in that case. Okay. And the direction of the magnetic field is related to the direction of the current. So the fields are circling around the current in that case. And if you have a direction of current through a wire, this is the magnetic field it produces. So you can determine the direction of magnetic field by using the right hand rule here. You use your right hand here, your thumb goes in the direction of the current in the wire, and your four fingers then will curve in the direction of the B field. Okay. So this is called a right hand rule here. To determine the direction of the magnetic field, there will be another right hand rule that we'll talk about later on that's used to determine the direction of magnetic force. Okay. But this magnetic field produced by the current carrying wire, you can imagine if you have larger current, the magnetic field will be larger. So it's proportional to the current there. It's inversely proportional to the distance that you are away from the wire. So if you are further away from wire, then it gets smaller. So B field is proportional to I, inversely proportional to R, okay, with a constant number, okay? And we'll talk about that constant number later, not today, but it's a constant number there. We'll talk about it, okay? So the source of current, as I mentioned, it's due to the electrons orbiting in the nucleus here. So for example, if you have hydrogen net, atom, so the electron is orbiting in that direction. Now, if you notice that electron is negatively charged, so then the current should be in the opposite direction of the motion of the electron in that way. So now you can use your right hand rule. Your thumb points in the direction of the current, which is in this direction, and your four fingers then will curve in that direction. Okay, so then that gives you the direction of the magnetic field. So it's in this direction over there, and then over here on this side as well. Okay. So in that case, now the current produced by this electron, it produces like an electric field like this, and then which is similar to a bar magnetic field of with a north pole and south pole. Okay, so magnetic field goes like in that direction. Okay. All right. So you have seen that these lines that indicate electric field lines, so those are called electric field lines to represent the direction and then also the magnitude of the magnetic field at a particular location. So these lines are very similar to electric field lines, but there is a difference between the two, okay? So for the magnetic field line, again, they are not real lines, they are just imaginary lines, help us to visualize the strength and direction of the field, okay? So the arrow will indicate the direction. So for magnetic fields, it's pointing from the south pole towards the north pole outside of the magnet, okay? Inside the magnet is going from then the south pole to the north pole, okay? So in that case, you can see magnetic field lines are actually closed lines, okay? Instead of for the electric field line, it's pointing from positive charge to negative charge, which is not a closed line. Okay. So fields inside the magnet and then outside the magnets are pointing in the you can say in the opposite direction. Outside the magnet is from north pole to south pole. Inside is from south pole to north pole. Okay. All right, and these lines, again, if you have magnetic fields around and they will never cross, similar is as in the electric field lines because um, at a particular location, you should just have one magnetic field strength, right? So if you have multiple ones, they should add up, okay? And again, the density of magnetic field at certain location is proportional to the density of magnetic field line. So you can see these lines are closer to each other. That means fields are stronger and over here than over here. These two are quite apart from each other. Okay. All right. Next, let's take a look on the magnetic field, and then if you have charged particles in the magnetic field. Okay, so this is again an experimental observation. So if you have charged particles moving in a magnetic field, so then there's a magnetic force on the charged particle, and it turns out to be proportional to the charge, okay, of the particle, and then how fast it's moving at, and then the magnetic field strength. Which is called B field. Okay, so B field for magnetic field, E field for electric field. So that's the symbol as commonly used for magnetic field. So the force of moving charge experience is equal to Q absolute value of QVB and times the sine of theta F. Theta is between the two vectors V and B, the velocity and B vector. Okay, so you can see there's an angle involved. So that means if velocity and B are in different orientations, then you get different magnitude of the field. Okay, so when V and B are perpendicular to each other, then you have maximum force because theta is equal to 90 in this case, and then sine of 90 is 1, is the maximum. When V and B are parallel to each other, then theta is 0. So then in that case, you get minimum force or no force, okay? Because force then will be 0. In general, force then is equal to just absolute value of VQ, QV, B sine theta, okay, if that's an angle. The magnetic force is also called as a Lorentz force because he's actually contribute to this field, okay, to a great extent. All right. And you can measure magnetic force and then also the charge and then the velocity, and then you can back calculate what will be the magnetic field. Okay, so that's an indirect way of measuring magnetic field. You can do that. For magnetic field, the SI unit is Tesla. Yeah, it's the car company Tesla. I guess it's named from a scientist called Tesla, which has a lot of contribution to the field. A couple hundred years ago, or maybe not quite 200 years ago, but 100 something years ago, probably. So we use symbol T for abbreviation. It's equivalent to Newton's divided by amps times meters. Okay, so Newton's comes here, amps from amps times meters from these two combined. Okay, so this is Coulomb times meters over second. So then Coulombs over second will be amps. Okay. All right. So the magnitude is QVB sine theta for the magnetic force. Now the direction, because force is a vector, so we need to also know the direction of it. We now use another right-hand rule. Okay, so this is called right-hand rule number 2, where you use your right hand again. Your forefingers points in the direction of the B field. Your thumb points in the direction of the V, the velocity. Then the palms facing in the direction of the force. Okay, and then this is to use on a positive charge. And if you have a negative charge, you still do it this way, but then at the end you flip your palm upside down. Okay, so then the direction your palm is facing then will be the direction of the force. Okay, for the charge particle. So you can see that positive charge will experience force that is in the opposite direction of negative charge. Okay. All right. So an example here. So there's a charge moving towards west here. B field, magnetic field is in this direction. So you put your forefingers in the direction of the B field, magnetic field, right? And your thumb in the direction of the velocity. Okay. So then your palm is facing down. So that's the force direction. Okay. So it's facing down in this case. All right. Now let's take a look on the example here. The first example of the day. So it says an electron moves at right angles to the magnetic field at 0.23 Tesla. What's the speed if the force exerted on it is 8.9 times 10 to the minus 15 newtons? Okay, so we are given B, we are given the F, and then we're looking for V. So we know that the force, a charged particle, in this case electron, is equal to, so Q, absolute value of QV B sine theta. Okay, and we are given F, all right, and we are given B field, and it says at right angle. So this guy is 90. Okay, so this guy is 90 degrees. So that means sine of 90 is 1. So you can just actually take this out. This guy is 1. You're looking for this V. And so we need to know Q, right? Do we know Q here in this case? You can pause and then think about it. The answer is yes, right? It says electron. Okay, so electron has a charge of electron charge, right? 1.6. And there's absolute value, so we'll just take the positive number, okay? So then, okay, so from given this equation, we know then V is going to be equal to F over absolute value of Q times B field. Okay, so it's algebra here. You rearrange terms, basically divide both sides by absolute value of Q times B. Okay, to get V. So then plug in numbers, 8.9 10 to the minus 15 newtons over. So we'll just take the positive number of that for the electron. It's a constant number, and then the B 0.23 Tesla. Okay, so V then turns out to be 2.4 times 10 to the fifth meters per second. Okay, so when you have everything in SI unit, your answer should also be in SI unit. Okay, all right, so that's that one. Now let's take a look at the motion of charged particles in electric field. Okay, so we know that if we have a charged particle in electric field, so in this case, in electric field, if it's positive charge, it's going to be experiencing this electric force pulling it downward. So if it goes perpendicular to the field initially, then it will be deflected. When it exits the electric field, it will be deflected at an angle. Okay. Now, in the magnetic field, so if this guy is perpendicular to the magnetic field, now the magnetic force F, we can decide the direction. We can determine the direction of that, right? Your thumb is going in the direction of the V, and your four fingers is pointing in the direction, so it's a little bit awkward, but like this way, okay? In the direction, your four fingers points in the direction of B field, your thumb in the direction of the V. So your palm is facing inward if we are starting at this location, right? So this is exactly equal or the perpendicular to the velocity. So anyway, when you look at your right-hand rule, right? So direction of velocity, direction of B field. So this is the direction of the F. So F is always perpendicular to the V, okay? The velocity. So in that case, we know that if you have a force that is perpendicular to velocity, so the speed, the magnitude of velocity is not changing. Only it changes the direction of the motion. So then in that case, this force will be a centripetal force. So the motion of the charged particle in the electric field should be then circular. Okay, if V and B are perpendicular to each other initially, so then it will be circular motion. Okay, instead of this, like in the electric field, it will be deflected in the angle. All right. So the application of this is in mainly in the science field that where you want to isolate a particle or you want to actually select a certain particle with a certain velocity. Okay, so you can isolate particles; they will have different velocities. But if you are looking at a particular velocity, or if you don't know, you can set up a combination of magnetic field and electric field. So then for the particles that will pass through here, you set it up so then for the magnetic force, which again, you can use your right hand rule again, B field is pointing from north pole to south pole in the configuration. So in that direction, invert. Now the charge is going in this direction, right? To the right. So your thumb is pointing to the right. So your palm is facing up. So B field then is going up there. Now your E field is pointing downward. Okay. So if these two are equal to each other, then the particle that has that particular velocity, which is, if set these two equal to each other, QVB equal to QE, so Q and Q changes, V then equal to E over B, and the particles with the velocity of E over B then will go straight because it does not experience a net force, okay? Particles with any other velocities will be deflected, either will have larger B field, F of B, or larger F of E, larger magnetic field force or larger electric force. It will be directed either upward or downward. Okay, so it will not pass through this device. Okay, so such a device is called a velocity selector. Okay, or you can use this to find the velocity of particles that goes through straight. Okay, let's take a look on this example here. Okay, so it says the velocity selector in the figure is designed to allow charged particles with a speed of 4.5 times 10 to the third meters per second to pass through undeflected. Find the direction and magnitude of the required electric field. Okay, so um, so in this case, in the figure, it shows there's a minus charge here. Okay, so charge is minus. So you can use your right hand rule. You can determine what's the direction of the minus charge here. Thumb is in the direction upward of the V field, and this guy, four fingers in the direction of the B field. So this is what you use for a positive charge, but now this is a negative charge. So this time your palm is facing in the positive y direction. So that means you have to flip it. Okay, so then your stance should be face or the direction of the magnetic field should be facing in the negative Q direction. Okay, so it should be then this is F of B. Okay, so for the electron or the negative charge particle not to be deflected, then we know that E will be in this direction. So F of E should be in this direction. Okay, F of E should be in this direction. But this is a negative charge, so that means electric field will be still in the opposite direction. So electric field should be in this direction. So then the force will be having in the positive y direction. Okay. So I think we have the direction of the electric field find out. Now we can work on the magnitude. Okay. So for this to be a velocity selector, these two velocities should equal to each other magnitude wise. Okay. And we know that V and B are perpendicular to each other. So for F of B, it's just Q V B. And then for this guy, the magnitude will be Q times E. And these two should be equal to each other. So you can say then my QE should be equal to my QVB. Okay. So you can see the Q actually cancels. So your E field then should be just equal to V times B. And we have both V. V is 4.5. So E is equal to 4.5 10 to the third. Okay. And then let me erase this. Okay. Ten to the third times the B field 0.96 Tesla. Okay. So then we'll find our E to be 4.3 times 10 to the third. And that will be in newtons over coulombs. Okay, that's the magnitude. The direction will be in the minus y direction. Okay, so that's the direction, minus y direction. All right. Okay. So since we know that the V velocity and magnetic field are perpendicular to each other, so then the charged particle will go in a circular motion here. So then the centripetal force is the magnetic force. Okay, so centripetal force, which is mv squared over r, is qvb. So in that case, you can see then if we know v and b, so then r will be determined. So r then will be equal to mv over qb. Rearrange the equation from here, so you can derive that r equal to mv over qb. Okay, so mv will be the momentum of the charged particle, Q will be the charge, and then B will be the magnetic field. Okay. All right. And just want to point out that the electric force will do work But magnetic force actually will not do work because V and B are perpendicular to each other. So force and displacement are perpendicular to each other. So there's no work done by the magnetic force. Okay. The other application is the mass spectrometer, which you can have charged particles entering the electric field with a known velocity. So somewhere here, you can put a velocity selector. So then you'll know the velocity here comes in the B field. And then when the charges come out, they will come out at different locations, which means a different radius of the semicircle, okay, on the other side. If you have the same, if you have isotopes with the same charge, but then you can distinguish which one is which isotope in that case. Just looking at the radii, then you'll figure out, okay? So examples, again here, it says find the radius of the orbit when an electron and a proton. Okay, both are charged 1, but electron is negative, proton is positive. Okay, both of them move perpendicular to the magnetic field of given strength. Okay, so we know B, and then speed. So B is given. So this is B field, and this guy is V. So it's asking the radius. Okay, so if you go a couple of slides back, you'll find that the radius will be equal to mv over qb. And then it's actually very easy to derive this. Okay, so I just set up that qvb equal to mv squared over r, right? Because circular motion magnetic force should be equal to the centripetal force, and you'll find this. So it's looking for the radius of electron and then the proton. So we are given V, B. Do we know mass and Q for the electron? Yes. Okay. So because mass of electron is a fundamental number, it's a constant number. Mass of electron or the charge of electron is also a fundamental number. And then the same for the mass of proton, it's a fundamental number. Okay, it's a constant number. So then we can just plug in. So for A, radius of the electron, it should be the mass of the electron, which is 9.11, 10 to the negative 31, okay? And V is given as 6.47 times 10 to the 5th meters per second, divided by the charge, 1.6, 10 to the negative 19, okay? This is 6 there. And then B field is 0.86 Tesla, okay? So this will give you 4.28 10 to the minus 6 meters, okay, for the electrons radius. For the proton, R sub P. So we will use the mass of the proton, 1.673 times 10 to the minus 27. That's in the SI units of kilograms. And then times the speed is the same thing, 6.45 10 to the 5th. Okay. Over the same charge, 1.6 10 to the minus 19. And then the same 0.86 Tesla of that. Okay. Magnetic force, magnetic field. So this gives you 7.87 times 10 to the minus 3. Okay. And that should be in meters of the SI unit. Okay. So the main difference is the mass difference. Okay, so this guy has larger mass than this. Okay, the rest are the same, but at the end you get different radius radii for the two. Okay. All right. So quickly sum up what we learned today. So we talk about magnets and magnetism and what causes a magnetic field, how to use magnetic field lines, And then we talk about the magnetic force, okay, and then so the magnetic force for charged particle moving inside the magnetic field, magnitude is given by this equation, and then you use the right-hand rule to determine the direction of it, okay. Magnetic field can be calculated once you know the force, okay, magnetic force. All right, so we'll stop here today, and then we'll come back at another time, okay. Bye.